first lesson of our 6th unit entitled Sequences and Series, otherwise known as discrete functions. In today's lesson, we're just going to do an introduction to what sequences are. We'll be looking at what a series is a bit later on in the unit, but to start off, the first few lessons will be revolved around sequences. So we're going to discuss a few definitions about sequences. You're going to learn a few new terms, and you're also going to learn some notation that goes along with writing and working with sequences. So to start off, we're going to first look at two different definitions and some new terminology for your mathematical brain. So the first is what a sequence is. And you have seen many sequences before, but you may not have known that that's what it's called. In general, a sequence is just an ordered list of numbers that are usually separated by commas. So you see sequences all the time. Someone lists someone's set of ages for a certain number of people. Maybe they'll say the ages are 9, 10, 11, and 12. But you may have also seen sequences some other places too. The other thing that we're going to define here is what a term is. Now when we talk about terms just in math, generally we talk about 3x is a term, or the number 9 is a term. But when we talk about sequences, we define a term to just be one of the numbers within the sequence. And this will become very important when we talk about different terms within a sequence. Like for instance, a sequence can have a set number of terms. If I'm talking about how many numbers or how many odd numbers exist between the numbers 1 to 100, we know that there are going to be 50 terms in that sequence of numbers if we wrote them all out. 1, 3, 5, 7, and so on all the way to 99. So term is defined as just one of the numbers within that sequence. So let's take a look at a sequence here. We have the numbers 1, 5, 9, 13, 17, and then we have this little ... right here. And what that ... just means that this continues on forever. So this just continues on. Of course, I don't want to write all infinite numbers that could exist within this sequence, so we write the ... So if I were to say what their position is in the sequence, well, the number 1 would be in position 1, the number 5 would be in position 2, and so on and so forth. Number 9 is in position 3, and 4, and then 5. That's pretty obvious to see in that sequence. So essentially, number 1 right here is term number 1 in the sequence, whereas number 13 is term number 4 in the sequence. And we use this notation, t and then subscript n, to represent the term number within the sequence. So number 1, not only is it in position number 1, but we call it term number 1, and we write the letter t subscript 1, which represents the first term in the sequence. Number 5 is the second term in the sequence, so we would call it t2. And number 9 would be t3, and so on and so forth. So if I asked you, what is t5 in this sequence, you would simply say 17. Tn represents just the nth term in the sequence. So, for instance, what if I asked you what the 12th term is in the sequence? Well, I would try to find t12. So n could represent any number within the sequence. This is also called the general term. So Tn is something we call the general term, normally represented as some sort of formula. We have some sort of formula to figure out what the nth term is in a sequence. Well, we'll get to that later. There are two types of sequences that we can have. One is a finite sequence, which has some end number. So the numbers 2, 4, 6, 8 all the way to 100, and it stops there. That would be a finite sequence. You could describe it as the even numbers starting from 1 all the way to 100. And an infinite sequence is just a sequence that does not have a set ending. So 1, 3, 5, 7, and then so on beyond that. It doesn't end at 99, it doesn't end at 199. This sequence, in fact, does not have an end. So like I was saying, this general term Tn can be expressed usually by a formula. And we note here that the n value in this formula that we're going to create, we say that n is always a member of the natural numbers. So this script looking n, when we were talking about domain and range, and we always said XER, where all the x values are members of the real number system. Well, that's the script version of writing the R for the real number system. Well, n is just the natural numbers, and the natural numbers exist. They're all positive numbers, no decimals, only whole numbers, from 1 to infinity. So 1, 2, 3, and so on until infinity. So n has to be one of those numbers. It can't be negative. It's impossible to have, to ask what is the negative fourth term in a sequence. That doesn't make sense. So we have this sequence started right here, 4, 8, 12, 16, and we can sort of understand where this pattern is going. It seems as though each number we are increasing by 4. So is there some sort of formula that we can use to express what the next number in the sequence will be, and then not only the next one, but what might the 20th number in the sequence be, or even the 50th number? There must be some formula that I could use to express this. And it turns out that there is. In a future lesson, we'll discuss how you can go about getting this formula. But I'll tell you right away that we can say that any number or any term in the sequence, so the nth term in this given sequence, is given by 4 plus 4 times n minus 1. Now this might take a little bit of understanding to see here, and I'm going to explain, but notice how the first term is 4. So if I wanted to find the first term, I would plug in 1 to where n goes. So the first term, t1, is equal to, and then I just rewrite it this formula, but put a 1 where the n goes. So 4 plus 4 times n, which is 1, minus 1, and we know 1 minus 1 is 0. And so look what happens. This turns to 0. 0 times 4 is 0, and I'm just left with my first term is equal to 4. That's exactly what we wanted. The second term here is 8, so t2 should equal 4 plus 4 times 2 minus 1. Well, we know that 2 minus 1 is equal to 1. And so 4 plus 4 is 8. And I hope that it might become more clear that each time we look for the next term in the sequence, this bracket right here increases by 1. So the next time t3, or the third term, will equal 4 plus 4 times 2. And 4 times 2 is 8, and 8 plus 4 is 12. And that's how this formula was sort of derived. In the very next lesson, we'll talk about sequences like this and how you can come up with an equation on your own. But we call this here the general term Tn. And this is also called an explicit formula. The definition of an explicit formula will come again later on in the unit. Let's take a look at another example. So given that the nth term, Tn, is equal to 3n plus 2, can we find the very first 3 terms in this sequence? Okay, so we know that the very first term in this sequence will be called t1. And t1 has an n value of 1. It's the very first position in the sequence. So we're going to throw a 1 into where we see n and solve. So 3 times 1 plus 2. And 3 times 1 is 3, add 2, and we get 5. So 5 is the very first term in the sequence. The second term in the sequence is t2, where n equals 2. So 3 times 2, and then add 2, we get 6 plus 2 is equal to 8. So the first term's 5, the second term's 8, and the third term, same process, but you might already see a pattern. It's going to be 3 times 3, because it's the third term, plus 2. 3 times 3 is 9, add 2 is 11. And so this sequence works where each term is just 3 more than the previous term. And I'll just put a little dot, dot, dot here to represent that this sequence does continue on. We can also write sequences using function notation instead of sequence notation, or this TN general term business. If I were to write this as function notation, I would write this as the function at n, or the nth term in the function. And it would be written out the same formula, 3n plus 2. So you could see that if I wanted the first term in the function, well, f at 1 would be equal to 3 times 1 plus 2, which is just equal to 5. And we would get the same pattern that we had up above. So function notation works the exact same way. And these all sequences are functions, well, at least these sequences are functions, because you only have one given value that each term in a sequence can be. So you can't say the fifth term in the sequence is equal to 5 and 7. That can't exist. Each sequence has their own pattern, and only one number fits into each given term. So that's why this is a function. It's like for any given x value, there's only one possible y value. Well, for any given n value, or any given number or term number in the sequence, there's only one possible number that could be. We call these discrete functions. They're not continuous functions, they're called discrete functions because the function doesn't exist between the n values. Remember, the n values are only whole numbers that are positive. So the function wouldn't exist for when n equals, let's say, 3.5. That wouldn't exist. So that's not a continuous function, we call it a discrete function. Let's look at another example. So what are the first 3 terms if given in function notation my sequence is f at n equals -5 to the exponent n minus 1? We're going to use the same process that we used before. So I'm going to find the function at 1, which is my first term. Function at 1 is going to equal -5 to the exponent n minus 1, and n is equal to 1, so 1 minus 1, which is 0. Well, we've talked about exponents that are 0. Any exponent that's 0, or anything to the exponent 0, is just equal to 1. So the very first term in our sequence is 1. The function at 2 is equal to -5 to the exponent 2 minus 1. Well, 2 minus 1 is 1, so -5 to the exponent 1 is equal to -5. And our function at 3, -5 to the exponent 3 minus 1, which is -5 to the exponent 3 minus 1 is 2, so -5 squared. The entire -5 is squared, so because a negative times negative is positive, we get positive 25. And so our sequence is going to be 1, -5, positive 25, and then it'll continue on. No one said a sequence had to be all positive numbers or even all negative numbers. You could go back and forth just like this one does. Let's look at a third example here, and for each of these 5 different examples, I want you to find the general term for each of them. Meaning I want you to create a formula or an equation where you can say Tn would equal this. It might take a little bit of trial and error and problem solving, but I want you to try to come up with 5 different equations for each of these sequences to come up with Tn. And then once you have that formula, I want you to find the 9th term in each sequence. So T9. I'll help you out with the first one, and then I want you to try the other 4. So my sequence for the first one is 6, 12, 18, and 24. Right away I'm going to try to figure out what my pattern is in the sequence. Well, I start with 6, and to get to 12 I multiply by 2, or I could think of it as adding 6. And you notice how when I go from 12 to 18 I didn't multiply by 2, but I did add 6 more. And each of these numbers are 6 more than before. So, if I keep multiplying by 6, I can generate a formula where the first term is just equal to 6. The second term is going to be equal to 6 plus 6. The third term is going to be equal to 6 plus 12. But that's the same thing as saying 6 plus 6 times 2. It's like I took the first term but added 2 more 6's to get to 18. And then the fourth term is going to be equal to 6 and then add 3 more 6's because it's 1 more 6 than before. And you can sort of see the pattern here. So my nth term is going to be equal to 6 plus, and then how many extra 6's am I going to need to add? Well, the very first term I didn't add any extra 6's. The second term I added 1 extra 6. The third term I added 2 extra 6's, and so on. It's always 1 less than the term number I'm talking about. So if my term number for the general term is n, I want to multiply n minus 1, or 1 less than the number or the term number that I'm looking for. So for t5, for example, I would take 6 and add it to 6 times 4, because 5 minus 1 is 4. And that would fit the pattern with the rest of it. So Tn is equal to 6 plus 6 times n minus 1. So if I now want to find T9, the ninth term in the sequence, well, that's going to equal 6 plus 6 times 1 less than the term number, so 8. 6 times 8 is 48. Add 6 more, and we're at 54. So the ninth term in this sequence is 54. And you can add this up for yourself to verify. Now I want you to try the other 4. Press pause on the video, try them out for yourselves, take about 5 or 10 minutes to go over them, and then hit play again and see if you are correct. Because in about 10 seconds of video time, I'm going to put all of the correct answers on. Afterwards, make sure you try all the questions in your homework, including the word problems. And there could even be some enrichment questions included in your homework as well. So try those out, and good luck. Here are the solutions to the other 4 examples written below. Not only have I included the general term, but also what the ninth term in the sequence is.